So let's take a look now at example 2, where we're going to have another instance where a U substitution is going to be very important. Remember that a U substitution is just an extra strategy that we have available to us when we come to an integral, but it doesn't mean that every integral requires a U sub. We should always still be running down our standard list of first checking to see if we can use our derivative rules in reverse, then checking to see if we can actually do any algebra simplifications, and then finally seeing if maybe a U sub will be helpful. So this is still the general plan of attack that we're going to be following. Now, of course, here when I look at this function, cotangent to the third of x times the cosecant squared of x, that is certainly not a derivative rule. And so I'm not going to even bother thinking or trying to work too hard on strategy 1. Here I'm actually going to recognize that actually doing a U substitution is going to be really nice, because I can see that there's something in here that when I take its derivative, the derivative is also inside of my integrand. Now, of course, since this is, again, a definite integral, I need to make sure that my function is going to be continuous. And indeed it is. On the interval from pi over 4 to pi over 3, the cotangent function is always defined. Remember that my cotangent would only ever be defined at a value of like 0 or at pi. And the cosecant function is always going to be defined, because that's only undefined also at values like 0 and pi. So I'll go ahead here and just say that we note that f of x, which is the cotangent cubed times the cosecant squared of x, is continuous on the interval from pi over 4 to pi over 3. So we can use the fundamental theorem of calculus part 2. Now, I'm going to go ahead and show you kind of a substitution here that I think would work out nicely. I could let u be equal to the cotangent of x. Notice here I have cotangent to the third, and so if I did this substitution in, I would have u to the third. And the reason that I like this substitution is because if I then calculate the derivative, du dx, that would be equal to a negative cosecant squared. And so, with a little bit of rewriting, I can get that negative du should be equal to the cosecant squared of x dx. So I can effectively replace everything at the back as well as what I have in the front. Now I have to remember that I also need to change the bounds. So I'll say our bounds become, and I can just swap this over again using my formula that changes x's into u's. So I'll change my lower bound by plugging in pi over 4. The cotangent of pi over 4 is the value of 1. I can also change over my value of pi over 3 by calculating that the cotangent of pi over 3 is going to be 1 over root 3, or if you want, you could write that as square root of 3 over 3. So let's go ahead and see what we're going to end up with here. I can see then that my integral that I had at the start, cotangent to the third of x, cosecant squared of x dx, will be transformed in the following way. Again, my lower bound is going to be changed to a 1. My upper bound will be changed to this 1 over root 3. I'm going to have now, instead of a cotangent to the third, since cotangent is the same as u, I'm going to end up with a u to the third power. And then my cosecant squared dx is going to be able to turn into a negative du. And I'll just put this negative here at the front, or I could even pull it outside the integral. Now, if I want to go ahead and do my antiderivative, this is going to be super simple. I'm just going to get negative a fourth, u to the fourth, and I evaluate from 1 up to 1 over root 3. So let's see, this is going to be negative a fourth times 1 over root 3 to the fourth power minus negative a fourth of 1 to the fourth power. So this is going to leave me with, let's see, if I take this quantity and I raise it to the fourth, that's going to be square root of 3 to the fourth, and I think that's going to end up as a value of 1 over 9. and then I get over here plus a value of 1/4. Now, I can easily see here this is going to get me negative 1 over 36. This would be the equivalent of 9 over 36, and so I'm going to end up with a grand total of 8 over 36, which if reduced you could write as 2/9. So this here would be the total area that's underneath the original curve on the given interval.